Chapter 12, Deflection of Beams and Shafts, Moment Area Theorem, Part B, Example 9. Let's review a very interesting example in moment area method. So it just says if we want to have a moment of a negative W L squared over 12 at point B at the center. For the beam shown below with a uniform distributed load uniformly apply at the entire span, and also we do have a spring at the center. So we want to determine the spring constant K for which the bending moment at B is given by the below. So if we just cut the beam by center by the point B, and we want to have a negative moment of a WL squared, and by negative we mean a moment which pulls the top and pushes the bottom. So that's a concept of a negative moment. So that's a moment which a positive moment is a moment which pushes the top and pulls the bottom, and vice versa is a negative moment. So if we have a such situation, it's a just a negative moment. And in that case, we just need to, and each section is goes by length of L. If we just develop the summation of moment about point B goes zero, considering a external moment, a given moment of a negative WL squared over 12. So in that case, if you develop and if you convert the distributed load for half of the beam, which is WL, because each section goes by length of L from the problem statement, so that's WL applied at the L over 2, mm, and that's a negative WL squared over 12 plus a WL times L over 2 and a positive one, mm, minus RA, which we already know what are we are going to calculate RAs. So if you if you make this moment about point B, it just gives you RA is equal to, because the only unknown is RA, it just gives you RA is 5 over 12 times WL. And due to symmetry of the structure, one can easily say RA is equal to RC at both support, and that's also is equal to 5 over 12 WL. Hmm? And yet by summation of force in y direction goes 0, it just gives you 2 WL, that's Fs, mhm, plus a 2 of the force should cancel out the, that's not 0, that's equal to 2WL. Uh-huh. And if you do the math, because all the forces, so this is RA, this is RC, and they are identical to each other. Each of them goes by 5 over WL, both of them, plus a force in a spring, because we have an F spring over here as well. And it should goes, it should cancel out the overall applied load at the top. That's 2WL. So that's what we have here. So if you do so, it just gives you Fs, force in a spring, is just a 7 over 6 WL. Hmm? And again, in a springs, we do have this relation. If we want to calculate the constant for a spring, so Fs is equal to Ks times delta S. So if we want to, for in our problem, we are looking to calculate a Ks. So far we know what Fs is. If we do calculate uh, Ks, delta S, we had we can easily calculate our constant of a spring. And to do so, we can apply a easy solution of a moment area theorem to get the answer. So we, as I already told, we all also know delta. So if F is equal to K times S, delta is Fs over Ks, and that's delta B because springs rest at the point B. So based on moment area method, if we just draw the shear diagram for half of the structure due to the symmetry, Ra is 512 times WL. We already saw we have a climb up by a Ra, no nothing, and it just, if this is only uh, forget about W for now, we are just drawing shear for Ra, then for W in the other part. So if load, if beam handles only Ra, there is no nothing to apply if you ignore W, and it just comes all the way to the center. So we have this area for V. And if you consider the effect of W, that's a constant, that's a linear constant in load goes a linear in shear. So that's the two part of this. Instead of having them combined together, we use the superposition uh, uh, rule to have them separately and add them up together. So that's the shear. And if you draw the moment from the shear, you can easily get for the top one, you can get a uh, area over here. It just goes by a triangle, and the linear one goes by a second degree curve. Mhm. So how that goes, and at the same time, we do know from the geometry that delta B is exactly equal to tangential deviation of A with respect to B. That's A with respect to B. That's exactly equal to delta B. So if we calculate tangent of A with respect to B, which is we can easily calculate that based on the area under moment, because that's what based on second moment area theorem, that's m over ei times x bar 1, which is calculated from point A. So let's see how to do that. Again, if we want to know the area under here is just a half of uh, L times, uh, sorry, L times, it's the rectangle, L times 5 WL over 12. So that's 5 over 12 WL squared over EI, which is the area under first part of shear goes here, not here, just here. And for the other one, which is a second degree curve, this amount goes by an area over here. So that's a WL squared over 2EI. This is a positive area, and the other one is a negative. Centroid for each part is just given. For the triangle, it's a 1/3 from the base, and for a second degree uh, uh, curve is a 1/4 of L from the base and 3/4 from the other side. So if we want to calculate the tangential deviation of A with respect to B, that's a m over EI calculated from this part, from point A. So that's A1, this positive area, uh-huh, plus the negative area of A2. Mhm. So A1 goes by 2/3 of L, A2 goes by a 3/4 of L. And just be careful, you have to subtract the two areas from each other. So a half of a 5 uh, WL squared over 12 EI, hmm, which is here, that's this distance, time L times the length, which is the area of this triangle, times 2/3 of L minus a 1/3, the area of uh, our curve, our second degree curve, a 1/3 of WL squared over 2EI times length over 3/4 of L. If you do the math, it gives you a 1 over 72, and simplify that, it's a 1 over 72 WL to the 4 over EI, and that's a TA with respect tangential deviation of A with respect to B. So that's, again, we know from geometry that's TA with respect to B is exactly delta B of at the center, which is exactly the same as a spring displacement, and that's a delta B, that's a WL to the force over 72 EI. As soon as we know W, that's a good part of this problem, is we also know delta B, as we talked about it, it's Fs over Ks. So if we call this equation 1 and this is 2, if 1 and 2 says, if you just rearrange the equation, rewrite it based on Ks, it just gives you the stiffness of a spring, which is force over delta. We already calculated the force based on uh, the equation relation, which is 7 over 6, if I'm not wrong, times WL over, yes, that's correct, over K WB, which just replaced from equation 1, WL to the fourth over 72. And if you do the math, it gives you 84 EI over L cubed, which is the stiffness of the spring based on this problem. So again, this example was asking about determine the spring constant K if MB is provided to be at the center. If you cut it through a negative WL squared over 12, you have moment at B. And based off solution 1, we get the delta at B, which is exactly the displacement of a spring, that's WL to the force over 72 EI, and also stiffness of a spring, which is 84 EI times 84 times EI over L cubed. In the next video, I'm going to solve this problem in a far simpler method, which calls the uh, displacement consistency of displacement, which just says the amount of deformation for beam uh, is exactly the deformation for a spring, because they are connected to each other and there is no other way to move at the same amount of displacement. And that's again delta B equal to WL to the 4 over 72 EI, and Ks is 84 EI over L cubed. Thank you.